Alright, so in this lesson we're going to look at work done by variable forces. So far we've only dealt with forces that are constant forces. And so in the graph above we have a force that's a variable force, and this force looks like it acts with a magnitude of 4 newtons for 12 meters, and then it looks like it linearly decreases from displacement of 12 meters to 20 meters from 4 to 0. And we want to figure out how can we find the work due to this force. Today we're going to kind of do the simplified version of this. When we get to later on in the year, we'll revisit work done by variable forces, and I'll show you another way to solve this that takes a little bit more mathematics to work through it. So above is a graph showing variable force as a function of displacement, and so the easiest way to do this is, say we want to find the work done on a 4 kilogram object as it moves from 0 to 20 meters. And if the object starts at rest, how fast is it moving at x equals 20 meters? So the way to do this is to find the area underneath the curve. So find the area in here between the 4 newtons and there. The nice thing is that this is a nice rectangle that is 4 newtons high and 12 meters wide. So that's 48 joules of work. On the right hand side, that's a nice triangle. So it's 8 meters long, 4 newtons high. Half base times height is a triangle, so 16 is the area of this. And so the net work done is really 48 plus 16, 64 joules. Now if I want to figure out what the change in kinetic energy is, or change in velocity, I could use work energy theorem. 64, the work done, is equal to change in kinetic energy. Luckily I've made my initial velocity 0, so that last term cancels out. And so I can solve this by multiplying both sides by 2, dividing by m, and then square rooting everything. What you find is that this object is moving at 5.66 meters per second at x equals 20 meters. So the second problem that I have, or the second question I have, deals with kind of leading into what I just said at the very beginning, that we'll look at this in a bit more detail later on this year and try to figure out how can we deal with variable forces in maybe a more elegant mathematical way than just finding the area under the curve. Some of you probably know where I'm getting at here. But to the right I have 5 graphs that are showing the force acting on an object as a function of that object's displacement, and I want to know which of those graphs represents the greatest change in kinetic energy for the object. So, I kind of gave you the answer, but what you want to find is which one has the greatest area under the curve. Now 3 of these, I would argue, are exactly the same, because 3 of them have an area of 2 blocks under the curve. Those 3 are A, B, and D. If you look at A and D, it's pretty obvious there's 2 blocks under the curve. 1, 2, 1, 2. B, there's 1, half plus another half is 2. So we're left with C and E. C looks like it has less than 2 blocks under the curve. This is less than a block. This is less than a block. That's less than a block. Maybe all 3 of these add up to be 1 block. I don't know. If we look at E, it for sure is 1 block. It has almost another block, and maybe about a quarter of a third block. So these 3 here definitely add up to be more than a block. They might add up to be almost 2 blocks. And so I think E is the best answer here. E has the greatest area underneath that curve. So like I said, we'll revisit more of these later in the year. And what we need to know is that there's some stuff from calculus that I want to make sure that you've been exposed to first before we get into this. We'll get into a little bit of calculus when we do this next time, and I think having some background makes that process a little bit easier in figuring out how do I set up my equation and how do I actually work that equation out. There are some tricks for doing that make your life easier that I think once you've seen it in calculus a couple of times, it becomes pretty easy to do this type of problem. So that's kind of a quick overview of work done by variable forces. Probably the most common variable force we're going to come across, at least at this point in time, would be the Hooke's Law spring force. I'll do a problem here in a little bit that deals with force due to a spring. We'll actually talk about that in a little bit more detail as we work through this class as well, and actually drive that and prove that that's the case when we talk about work done by variable forces later.